Okay, so let's go on to 28.4. So 28.4, this is the electric potential. So we would use the same approach we use for defining the electric field to define the electric potential. So I'll remind you of that. So recall that when we defined the electric field, we used the source charges, or the source charge, and the test charge. So we said the electric field, I'll just write E field, is defined as the force of source charges on a unit test charge. So this is defined as the electric force of a source charge on a test charge. So we had E equals force from source charges divided by the test charge Q. Okay. So this was our definition of the electric field, and the unit was newtons per coulomb. We will do the same to define electric potential. So electric potential has a letter symbol V, and it's a scalar quantity. So we start off by using that approach, which I say it is a scalar quantity. So electric potential has a letter V. It's a scalar quantity, and is defined as the potential energy of a charge Q plus other source charges relative to the charge Q. So we can say the potential V is equal to the potential energy of Q plus sources divided by Q. So we can write the potential. So potential is potential energy of Q plus sources divided by Q, and so potential energy Q plus sources is therefore equal to Q times V. That's another way of writing it. So the unit of electric potential is the joule per coulomb. So 1 volt is equal to 1 joule over 1 coulomb. So we shall use volt as the unit of electric potential, and we should remember that it's equal to the joule per coulomb. Okay, so what is it?
IV?
1J, it's 1 volt
or 1
is equal to 1 joule over 1 coulomb. So let's go on to the parallel plate capacitor so that we'll see how potential works, and then we'll get some quick diagrams of that. So in 28.5, potential inside a parallel plate capacitor. So we've already talked about capacitors at some point, and we said a capacitor is a device for storing charge. So I'll remind you of that. It also has a uniform electric field.
Storing charge.
For storing charge. So it stores charge. And the electric field in between the plates of the capacitor is eta over epsilon naught, if you recall. It's a uniform electric field. So it's given by the Greek letter eta over epsilon. So let's look at a capacitor. So we have the capacitor plates like that. And we can store charge on the capacitor by connecting a battery across the plates of the capacitor. So we have the negative terminal and the positive terminal of the battery here. So this will acquire a positive charge, and it will have positive charges all along. This will be the negative plate. And so the electric field will go from this plate to this plate like that. And it will be a uniform electric field. So let's say that the distance between the plates is D, and the potential, let's do the electric field first. The electric field is E. So we have an electric field E and a distance D between the plates. Potential energy U is equal to the charge Q times potential V. So we already know that, where V is the potential. So suppose we put a charge in between the plates of the capacitor, and it will have the energy U. Okay, so that energy U is just equal to Q times V. We also know that the energy U is just equal to the work done, which is equal to force times distance. And so we shall use that to determine what the actual B is in the parallel plate. So W is equal to force times distance. I'm going to use distance D, but at some point I think they use D also here, but they're starting S equals 0 to S equals, but we can use D. So note that F is equal to Q times E. Therefore, U is equal to Q E times D, meaning that we can write V equals ED. So the potential between the plates is equal to the electric field times the distance between the plates. So V is equal to ED. In your text they use S, but I think it's still the same. So V is the potential between the plates and it's equal to E times D. So we can illustrate this as below. So we have our plates again. The distance between the plates is D. I'll leave the battery out this time. I'll say that this is plus and this is minus. So this is V plus and V minus. Okay. So when you put a charge between the plates, suppose you put a positive charge, it's going to be repelled by this plate and it will travel to that plate. Okay. So in this case, its potential is going to drop because it's going from the positive to the negative plate. Its potential will drop. So we can say that if a positive charge is placed at a point close to V plus, it travels to V minus, so it loses potential energy. So it's basically like if you take an object and you drop it in the gravitational field. If you drop it from a high point, as it's going down, it's losing gravitational energy. The same way, if I take something and I put it next to the positive terminal, it's going to fall towards the negative, so it loses potential, electrical potential energy. So you can say its potential energy decreases. So we can say that since we have V equals E times D, we can rewrite this as E equals V over D, or delta V over D, where delta V is just equal to V plus minus V minus. The reason why we use V initially is because typically one of the plates is at zero potential and the other one is at the high potential. So we can use V over D, or if you want to use delta V over delta D, that will be fine also. So let's say that we have the plates like that again. This is, if we were to connect this to, let's say, a 9-volt battery, and this will be 0, and this will be 9. Okay, so this will be V minus, and this is V plus. So delta V is equal to V plus minus V minus, which will just be equal to 9 volts minus 0, so it's equal to 9. So you can say delta V is equal to V, okay, if you think of it that way. And so between the plates, you can have potential lines that way. Let me see how I can divide this up. So 0, in the calculator. If I divide it into 2, then I guess, or if I divide it into 3, then I can just use 0. This will be 3. So we can say this is 3, this is 6, and that's 9. So the potential lines are 3 volts, 6 volts, and 9 volts. They haven't done it as well as I should, but basically you can divide this plate into those potential zones. And so at each point you can have an equipotential line. And then I can also divide from 0 to 3 into 1.5. Between 3 to 6, I can put another 4.5. I can put a point here which is 4.5, and so on. But just to illustrate the point, so there are equipotential lines between the plates that go from 0 volts to 9 volts. Okay, and so the potential rises that way. Say that's your potential rise from 0 to 9 volts. The next thing I'd like to do, let me look at the equipotential lines and how they relate to field lines. So we can say that the broken lines between the parallel plates are called equipotential lines. Equipotential means equal potential, so they're called equipotential lines. We shall see next the relationship between equipotential and field line. So we can say again, we consider the capacitor below. So we have a capacitor again, and so this is a positive plate and a negative plate. So the electric field goes this way from left to right, and perpendicular to that electric field is the equipotential line. So we can say that equipotential lines are perpendicular to field line. Let's look at the equipotential lines of some charge distributions. So we have a positive charge like that and a negative charge. So we know that the electric field goes this way between the charges. Note that the electric field lines should not cross. So then we will see that the equipotential line at the center should be pretty straight like that. And then it should start curving a little bit this way. And all of this is done with the expectation that the equipotential lines are perpendicular to the field line. So you can see that it becomes more curved as you get closer to the charge itself. I'll try to be as symmetric as I can. So this is how it should look when you have equipotential lines and field lines. Okay, let's try an example before we go. Actually, let me give you one of these to try. So let's say you have two positive charges. Draw the field lines and equipotential lines for these two charges. Okay, so I've given you two to try. Let me put the second one here. So two. So you have a positive charge, and I put it next to a sheet of negative charge. Okay, so I've given you another exercise there to try. Okay, let's continue. So what we have here for number one, so there are solutions. Let's put solutions. So for number one, I gave you two positive charges. And so we said that the field goes away from the positive charges. So I usually start that way, and then you go this way. And then when you are getting to the middle, you go like that. And you try to be symmetric. And the same thing for this one. You should go that way and this way. So again, the field line should never cross. So that tells us that once we're getting close, we should have something like that. And then we can say that the potential lines are perpendicular to the field lines. So what you have here, you have something that goes like that. And this would probably go smear up this way. The same thing for here. So that's what it should look like. So on the second one, number two, this is the charge Q. It's the positive charge. And then you have a negative sheet. So what do you think the field lines are going to look like? So at this point here, you're going to have parallel equipotential lines, and the equipotential lines are going to go like that. And that one was not very good. As it gets closer to the charge, it's going to be more curved. So you're going to have something that looks more like that. And that's how the equipotential lines should look. And then the third exercise there, we have a parallel plate capacitor with 70 millivolts between the plates. So force is given by Q times E, right? And E is what? What is the electric field between the parallel plates of the capacitor? Formula for E, or at least for the parallel plate, we know that E is, yeah. You're right, go ahead.
Be over D.
D, yes.
Yeah.
So we have delta V, we have D, and we have charge. So you just calculate F. F is equal to Q delta V over D, at least for the charge between the plates of the parallel plate capacitor. So you need to find E. E is equal to delta V, which is 70 millivolts, or 70 times 10 to negative 3 volts. And then you divide that by 2 millimeters, which is 2 times 10 to negative 3 meters. So the negative 10 to negative 3's cancel out, so E is 35 volts per meter. And then, so F is equal to Q times E, so 5 times 10 to negative 6 coulombs times 35 volts. 35 volts per meter, of course. So this would be 175 times 10 to negative 6 newtons. So you can say 1.75 times 10 to negative 4 newtons. So we can go on. Let's go on to look at the electric potential of a point charge. So this is 28.6. Okay, electric potential of point charges. Let's say that suppose we have point charge Q at some point in space. So we have Q here. Then what we can say is that the Q produces an electric field, of course. It will produce an electric field all around it. If we place a test charge at some point here, let's call this test charge Q prime, then the test charge Q prime experiences a force F, which is equal to the charge Q times the electric field E, where E is the field due to the source charge Q. So we can say that the potential energy delta U of the system of source charge Q and test charge Q prime is given by delta U. That's our potential energy delta U. Delta U is equal to minus W, where W is the work done, which is the integral of F dot ds, force times distance, where F is the force on the source charge, the force on the test charge due to the source, and ds is the distance moved by the test charge. So what we can do then is to find that the work W is equal to integral of F dot ds, which can be written as integral of Q E dot ds. Okay, so that's another way of writing it. So work is equal to that, and then from that we can get our potential energy. So suppose the charge moves from one point, let's say position 1 to position 2, we can integrate it that way. So since delta U is equal to minus W, or since W is negative delta U, we can say the potential energy of this system is equal to minus Q integral from a certain point 1 to a certain point 2 of E dot ds. So that's the potential energy of the system. And we also found that the electric potential V, and we can use delta V, electric potential, or let me use electric potential V, is defined as follows. So we already did it, so I'll just quote that V we said was equal to delta U over Q. So the potential V is therefore equal to minus Q. So potential V is going to be equal to the potential energy over Q. So it's equal to minus Q integral from 1 to 2 of E dot ds over Q. So this is going to be minus integral from 1 to 2 of E dot ds. Okay, so this gives us what we found earlier for the parallel plate capacitor. We saw that the potential V is equal to E dot ed, or E dot, suppose that the ds is equal to d, then we have E dot d. So if we are going from 0 to d, then we shall have the positive ed. Okay, so this is what we found earlier. So we can use this to find the potential energy of a point charge, and I'll find that in a minute. So for a point charge, the potential V is V equals K Q over R. So this is the potential of a point charge. Okay, so example, a 5 microcoulomb point charge Q is at a point in space. What is the electric potential at some distance of 5 millimeters from the charge? So calculate the electric potential at some distance from the charge. So you should be able to use the formula that we've just come up with to calculate the potential of the charge Q at some point, a distance from the charge. So potential V is equal to K Q over R. So you have a charge Q here, and we are finding the potential at some point, some distance R from the charge. That potential is only due to the charge Q. It doesn't depend upon the probe or the test charge. It only depends on the source charge Q. So the potential V is equal to 8.99 times 10 to the power 9 times the charge, which is 5 microcoulombs, is 5 times 10 to negative 6 divided by R, which is 5 times 10 to negative 3. So that should come out pretty well, 8.99 times 10 to 6 volts. So let me see, I think I need to make a correction somewhere along here, because I called one of this a source charge potential of the system. So source charge Q and test charge Q prime. Okay, so this charge is going to be your test charge Q prime. So the electric field is acting on the test charge Q prime. So make that correction. The charge in the integral is Q prime, not Q. The source is Q and the probe or the test is Q prime. The force is going to be equal to the charge times the electric field. The electric field is due to the source, and Q prime is the test. Okay, so this is Q prime here also. So the potential then will be given, the potential energy delta U is going to be K Q and Q prime over R, which is going to be potential energy over Q prime. Q prime is going to be that. So it's going to be K Q prime over R times Q prime. So those two cancel out. That's why we ended up with this formula. So this is Q prime over Q prime. Okay, so make that addition here. Delta U is equal to that. This is something we found earlier for different charges. And V is delta U over the Q prime. So K Q prime over R times Q prime. Q primes cancel out. So the potential V, which is this one here, is minus Q prime, which is the test charge divided by Q prime, and that's coming from up here. So I wanted to clarify that because we have several things going on there. There are source charges and test charges, and so we need to get those straight. So the formula is the same, it's still the correct. So the potential is due to the source charge alone. There is no test charge involved. So V is equal to KQ over R. Okay. So I think we can stop here.